In this video, we want to learn about the correlation. So sometimes we have like two variables, let's say, or more than two variables, and they are related to each other in a linear way. For example, look at here, we have the conversion here and the reaction time. So you can see that they're related to each other. Or we have the viscosity and temperature that they're related to each other like this. So in this situations, we would say that we have correlations. Correlations reminds us the covariance. When we are, it's like that when you think about it, it's like it brings covariance to the mind. But let's learn a little more about it. So with the correlation, we show it by R. And if you square it, it's going to give you the R square, like the same R square that we had before, determination of the coefficient of determination or determination coefficient. So if you have heard it before, it's exactly the same, like we have R here. A measure of the strength of the linear relation between two variables, X and Y, is given by the sample correlation coefficient. And you can look at here is X minus X bar and Y minus Y bar. So we are looking for X and Y, right? So the relation between them. And then we have the square root of the like X minus X bar power 2 and the Y minus Y power 2. So the only thing here is that R can be negative as well, because X minus X bar and Y minus Y bar here, this when we multiply these two and add, like sum them, like for all of the data points, this one can be negative. So we can have R as negative, like a correlation factor as negative as well. Oh, it's written here, can range from -1 to 1, represent a stronger positive or negative correlation as it gets closer to the positive or negative one. And when you think about it, when we are closer to 1 for R, when we have the R square, so we would have the closer to 100 or 1 as 100% or 1 as well. So it's going to give us a better regression fit as well. So as an indicator of linear associations only. So let's have a few examples. Here, the first one, if I ask you what's the correlation of this one, what would you say? You can pause the video and think about it. Go back to and look at the equation that we had in the previous page, and then you can come back and listen or look, like watch the rest of the video. Here, first of all, they have a very like perfect linear relation together. When you are looking at it, it's like a straight line if you put it. And because if we increase one of them, the other one is going to decrease. So we would say that for this one, the correlation R is equal to -1. For this one, if we increase one of them, the other one is going to increase as well. So the correlation factor here is going to be +1. We have two more examples as well. So here, for this one, when you're looking at it, there is no linear relation between them. So we would say they are unrelated and they are uncorrelated. So the correlation factor is going to be 0. But be careful here when we are looking at it, the correlation, they're uncorrelated. So it's like that, there is no linear relation between them, right? But they are related to each other. But still, because we can't have like a line like that, like a straight line to connect them. So the correlation factor for this one is going to be 0 as well, like R is going to be 0. If we had we can have like other examples as well. Like for example, you could have dots in a circle as well. Again, this is like half circle, right? Again, the correlation factor would be 0. Or for example, you could have consider a square, and then you could have like dots over there as well. So again, the correlation factor would be 0 as well. Just remember this, correlation doesn't necessarily imply the causation. So it is, for example, look at this. You can say that it's the one of like X is as a result of Y. Maybe sometimes it does not necessarily imply. So sometimes maybe we would have it, maybe we would not. It's not that definitely you would say that one is the cause of the another one. One factor is the cause of the another factor. So a plot of the population at the end of the Oldenburg, at the end of each year, against the number of storks observed in the year 903 to 1936. So when you are looking at it, you can say that these, like from up to here, like up to 200, we have like a correlation, like we can have a linear relation up to here, but you can't say one is the cause of another one, right? This is another like figure. So this is degrees in Fahrenheit and it's degrees in Celsius. So we would say that we can have like, this is another good example in my opinion. There is no causation here, but they are correlated, they're highly correlated. And we have the equation. So whenever we have the correlation factor close to 1, we can have a regression, right? Linear regression model for it. And we call it simple, and you can see there is a simple linear regression that comes to the picture. So when we say regression models, we talked about that quickly before. We have two different types of models. We would say models, they are mechanistic, or we have models like mathematical models, modeling, mechanistic models, or the empirical models. So empirical models are the same as the regression models. So we need to have data, and we will build our models based on the observations or historical data or design experiment. Like we are going to generate more data, but based on the models, the models that we have are based on the data points that we would get from like 10 years ago. Like they would say, we have a rule of thumb, you want to have a model that would work for 20 years, get data for 20 years, for example. Forecasting models that we have, for example. But all of these regression models are the ones that we would have regressor. So this one, we call this X, like the variable that we have here, and the X is independent variable, Y depends on X. When we define it, you can play with it. For example, you can make TC here, like move it, put the TF over there. So it's how you would define it. Depends that in your experiment, what's the main output that you are looking for. Like, for example, you want to sell a product to the customer based on customer's expectation or your product specification, what will be the output, for example. And some relationships are close to linear, but are not exact due to experimental error that we would have because of the experimental error. But for example, now when we have something like this is a review, and we are going to talk about it in chapter 2 a lot again, but you can look at it like in CHE 220 chapter 11. It's going to go through all the proofs that we have for how can we have the best fitted model for this one. And basically it's like this. You're going to have a straight line for the linear, right? How can we make sure that you have the best straight line? You would choose the best one. So this is the best one. Like this is one of the lines that we can have, but I can have another line like this as well, right? So what would we do? Look at here. This is the red line is my regression model. The dots are the real value. So if I get the difference, like vertical line from the vertical distance, from my real value, real data, and the forecasted point, that's my error, right? So I want to have a model which has the lower amount of the error. If you want a smallest error comparing to the other like lines, I'm going to choose a line. It makes sense that we would have the smaller one. But because here the lines, like for example, this one is going to be positive, this one is going to be negative, this one is positive, this one is negative, negative. What we would do, we are going to square all of these distance and then add them together. We call this method least square method. It's like least square, and these vertical lines that I said, we call them residuals. So it's that least square of the amount. We are going to choose a line which has the minimum amount of the like when we add the residuals, like a square of the residuals together, it's going to give us the minimum one. So we call least square method, the one that we have it. And we talked about that a lot in like chapter 11 in CHE 220, like in the basic studies. So mathematically, we can accomplish this by minimizing the sum of the squares of the residuals or the errors. And we would say sum of the square of the error is going to be sigma y minus y estimate, right? So y is the real data, y estimate is the result of the regression. So this difference that you see here is it's that vertical deviation that I showed you in the previous slide. We show it by SE2 as well, like the residuals as 2. And this one is sum of a square of error, or sum of a square of the residuals. So the slope and intercept, respectively, we want to, when we want to find out the slope and intercept. So what are we going to do is that we want to minimize this sigma E2. As I said, the proof, how can we prove this? It's if you go and look at the lecture notes of the chapter 11 of CHE 220 or any stats basic applied stats course, you can see the proof of this. But it's very simple. It's like that we want to minimize this SSE, right? And when you want to minimize it, what are you going to do? You're going to get the derivative and then make the derivative, put the derivative, like put it like equal to 0, say that it's going to be equal to 0, and then find the like whatever variable that you're looking for. So when you do that, so instead of y and y estimate, instead of y, you're going to put ax plus b, and instead of the y estimate, you're going to put the value that you would have, right, for the fitted model. And then you will minimize it. The only thing is that be careful, because you have the A and B estimate. These are the one that you want to find out for your model. So when you want to get the derivative, if you wanted to do that by yourself, you would need to get the partial derivatives, because you have two variables of the A and B here that you want to solve it. So you would get the partial derivative of the SSE respect to A, like A estimate, and then respect to B, and then you are going to find out A estimate and the B estimate. And this is the equation of the A and B, for the A and B that we would find. When let's say we drew our model, and we have another, you can call it like another properties that we can use a lot when we are working with the simple linear regression. So we can explain the regression in terms of variability in the data accounted for by the model. So this y is y bar. Y bar is the average of the y, right? It's the mean. So it's very important. So if you want to find out y minus y bar, which we want to always do that, we can say that is equal to the, look what we did here. It's like that we just added and removed y estimate. So it's like, so it's y minus y bar plus y estimate minus y estimate. If you do that, it's just a mathematics. So it's like that, it's going to be y estimate minus y bar plus y minus y estimate. So this y estimate minus y bar, always try to imagine that like in your brain, or try to, when you have it, like when you have the figure in front of you, say that, okay, what does it mean y estimate minus y bar? So here y estimate is that whatever estimate that you have underlined. For example, if the point that I'm looking for, like this is the data point, this point, so y estimate is going to be here. In fact, it's like this, the distance from this like estimate here to the y bar plus the distance between, like the difference between y minus y estimate. So here y is going to be this, y is the real value, minus y estimate, so it's going to be negative. It's going to give you y minus y bar, it's going to give you this. So in fact, what does it say? It says that this value plus this value, it should be equal to the total of that. Or you can say this total, right, like y estimate minus y bar, plus this negative of this value, it should give you this value. So we can say that this is true. With this one, we can expand it a little. As I said, these are all reviews. We can expand it a little and square it, and then we can say that sum of a square of the total is like that. All of those small deviations that I showed, we just square them and add them. It's going to be equal to the sum of a square of error plus sum of a square of the regression. So we would call the y estimate minus y bar power 2. We call this one sum of a square of the regression, because basically this is the y estimate is a result of the regression line. So this equation, like SST is equal to SSR plus SSE, is very important. It's super important, because we are going to find out the R square, coefficient of determination from it. So far we would say sum of the square of total is equal to the sum of the square of the regression plus sum of the square of the error. The next one, when we are working with the regression model, the next important section is like the analysis of variance. For working with it's like the same inference that we had for the like hypothesis testing and confidence interval that we had. So we are going to define a F test statistic here. So this F, MSR over MSE, is the test statistic. In the next video, I'm going to talk about this analysis of variance. So far, just know that correlation, what is correlation, and the correlation caused the simple linear regression, and we calculate the simple linear regression like with the for the simple linear regression models. We found them with the method of the least square method.